Good morning, everyone. Welcome to our next physics lecture. Okay, so let's just get started. So today is lecture number 26. We are still on chapter 13. No additional readings in the book at the moment. And you have your homework due whenever I said it was due, Monday, I believe. So I'm not gonna write anything else because there's nothing else really to write right now. Today we're going to continue to go over the gravitational potential, and we're going to learn about something called the effective potential, which I do not believe is in the book. So you're getting some a little extra knowledge. And we're going to talk about the gravitational field. So let's start off with reviewing a little bit from last class. So we saw last class that if we want to talk about the gravitational potential energy of a gravitating body and a smaller body, we can write that by taking the integral of du, right, which we know is going to be related to g m or r squared. So we take the integral of that and we get u sub g, right, the gravitational potential energy, equal to negative g m over r. And then we saw that if we want to draw that, it looks sort of like this. Right? This is the gravitational potential well, right? This is the well where it goes down to, in principle, infinity if we have two point particles, of course, which is not totally physical, but a good approximation most of the time. So we fall into this gravitational well as we get closer to the origin, right? Which is closer to those two gravitating bodies being next to each other. And as we go further and further out, we approach potential energy equal to 0, which in this case is how we have defined the maximum amount of gravitational potential energy, 0, right? And we can do that because when we take this integral, we have some u naught, and this additional constant energy is the thing that allows us to sort of shift this diagram anywhere we want in space, and also shows us that it's not absolute energies that are the important thing, it is relative energies, right? Because we would be adding and subtracting this u naught from whatever equations we were using to calculate energy. Okay. So, looking at this picture doesn't give us the whole story, right? Because there's other types of energies in this system. So, recall that if we have a circular orbit, or when we're only talking about the tangential velocity, right, we can have kinetic energy as well, not just gravitational potential energy, but also kinetic energy, which we normally define 1/2 mv squared. So now I'm going to add an additional label to this. I'm going to add a little t. So we're really, for this kinetic energy, we're just talking about the tangential kinetic energy that system has. So we think about something that's going around on an orbit, right? We're only talking about this vt as it goes around on this circular orbit. Now if I have an elliptical orbit, something like that, I'm not just going to have the tangential velocity, I'm also going to have some velocity pointing towards the center, some centripetal velocity. But if we take the case of a perfect circle, then we have only the tangential velocity, right? If we have a circular orbit, of course, for it to remain on that circle, right, it can't be moving in the centripetal direction at all, either in or out. So if we combine this tangential kinetic energy with our gravitational potential energy, we get to a potential energy that's called the effective potential. And that effective potential is kT minus gmm over r. So what we've done is taken the kinetic energy from the tangential component of that orbit and stuck it in with the potential energy, the gravitational potential energy, and we're going to call this the effective potential. So if you wanted to give this a name, you might call it the effective potential energy. Or rather, let's put potential energy in quotes. Potential energy. Okay. So we glob these two things together, and it's not really a potential energy because it includes a kinetic term, but we call it the effective potential energy because it allows us to see the dynamics of an orbital system very clearly, as if we treat this as if it was a potential energy. So that's why it's called an effective potential energy. Okay. Maybe I'll just write one more line, and this is something we saw a little bit of last class, is that if we want to write this in terms of angular momentum, we can write this as L squared, the angular momentum, over 2 big mass R. Okay? And then we would subtract off this G, M, R. Okay? Oops, excuse me, there should be an R squared there. R squared. Okay. So, you want to know where this equation came from, that this tangential kinetic energy is L squared divided by 2m R squared. Well, realize that if I have a circular orbit over here, the angular momentum is just mRV, right? If we have L equals R cross P, that R is this R here, and then that cross P, that's just mV. And for a circular orbit, I've always got a right angle there, so that sine 90 degrees is 1. So we have the angular momentum mRV, and if we plug mRV here, we have m squared over r, or m squared, r squared, v squared over 2m r squared, right? The r's cancel out. One of the m's in the denominator cancels with this m, and then we've got 1/2 mv squared. Okay, so that would give us this 1/2 mv squared term. But because I've defined angular momentum in this way, mRV, right, for a circular orbit, this means that this only accounts for the tangential kinetic energy, right? So why write it this way? Well, we saw last class that because we have the gravitational force only ever points in the centripetal direction, essentially, points towards the center of the gravitating system, that this angular momentum is always constant because r cross f, the torque, is 0 because those vectors are parallel, they're pointing in the same direction. So L squared in gravitational system is a constant. M, of course, is a constant. Note that this is the gravitation of the gravitating body, right? The big mass. Okay. So this is all constants except for this r squared. And the next thing you'll notice is that I have opposite signs on each of these terms. Okay. So what we effectively have is, in the effective potential, 2 opposing forces. So let's graph that out. So I'll just write it again at the top. Effective potential as a function of the radius, right, as a function of the distance between the gravitating body and the thing that's orbiting around it, is going to be equal to L squared 2m r squared minus gm over r. Okay. Let's switch colors randomly. So if we graph this, well, let's think about it a little bit first. So if we graph this, we've seen that this guy looks like that. Okay. And what does this guy here look like? Well, it approaches an asymptote as we get to r equals 0, right? It goes to infinity as r goes to 0, right? And it it dies off as r gets larger and larger. If we take r to infinity, we just get 0. So we have similar to over here, except flipped around, and this rises a bit more quickly because this is r squared and this is r. So let's draw this guy here. So this looks like that. So what happens when we add these two? Well, then our effective potential looks like this. Okay, so this of course is radius, and this is u effective as a function of r. Okay. So if you think back, I think I talked about this maybe a class or two ago. Whenever we have a potential energy in some system, we have a force. Or rather, I should say, if we have a potential energy that varies with position, then we have some force that's given by the negative of the first differential of that potential energy with respect to position. Right? So if you think about it, imagine this is a weirdly shaped mountain range, like a valley or something. Well, I can imagine my potential energy as a little mountain climber on this potential energy landscape. And of course, this mountain climber is going to feel a force that points in the opposite direction of the slope. Right? If you're climbing up a mountain, you feel a force, unfortunately, pushing you off the mountain. Right? If you imagine that the mountain was slippery, you would slide down the mountain, you would feel a force in the direction of the slope of that potential energy. If you were down here, at the bottom in this valley, you know, the safest place to be. By the way, mountains are just as beautiful from the bottom as they are from the top. I don't know why people bother to go up mountains. I've gone up several in my life, but it's okay, you know. But at the bottom of the mountain, there's lots of little streams and forests, and it's just as pretty. Why go up to the top? Anyway, so if you're at the bottom here, where you have zero slope, you don't feel any forces, right? You're in a state of equilibrium, right? The force that's pushing you this way is balanced against the force that's pushing you that way. So this is the same if we're in an orbital system. Instead of having a mountain climber, right, we have a planet feeling the gravitational field. Okay, so the traditional regular gravitational field, right, is just this term over here, which always wants you to be closer to the gravitating body. But we have this counteracting force that's related to the tangential kinetic energy, right? If we get closer and closer and closer to the gravitating body, we feel a force that's going to push us back outwards. Right? This may seem a little counterintuitive. You might think, well, wouldn't I as I get closer to the gravitating body, wouldn't I just accelerate right into it? Well, not if we have some angular momentum. Not if we're not moving directly towards the gravitating body. What if we're coming at it from kind of an angle, right? And then we saw when we were talking about Kepler's second law, that orbits sweep out equal areas at equal times, as we get closer to that gravitating body, right, our velocity total increases, and that kind of is going to want to slingshot us out and away from the gravitating body. Right? So this is, if you follow space exploration at all, this is sort of a standard technique in space exploration. Right? If you want your space probe to go at a faster velocity, one of the things you can do is get a gravitational assist from a planet. Right? You send your probe in and it swings around, picking up angular momentum from that planet and zooming back out. Right? So that's an open orbit, but it works the same even in a closed orbit. As we get closer, right, we get a higher velocity, which is going to want to fling us back out into the other part of the orbit. And of course, if we have an elliptical orbit, we see this happen cyclically. Right? So those are the two counterbalancing forces that we have inside of an orbit. Right? And now by looking at this energy diagram, you can see where those orbital shapes come from. Right? Imagine that we're at this minimum energy state here. Okay? So this would be a planet on a circular orbit. This radius between the gravitating body and the planet never changes, right? So that is when we have a circular orbit. It just goes around and around and around. It just stays in this little valley in our effective potential energy diagram. Okay, it's very stable there. It's in an equilibrium, and the R doesn't go back and forth. It just goes around and around, and our centripetal velocity never changes. Okay. Now, what if we have some intermediary state of energy? Well, look at where this line of energy intersects this effective potential. We have a close intersection, right, where that object is closest to the gravitating body, and we have a furthest part when it's as far away from the gravitating body as it can get. So if this object that's going around in orbit gets really close to the gravitating body, it feels this really strong force, right? This is a really steep line, really high slope, lots of force pushing it back out that way, and then when it gets out this way, right, that force from this term of the effective potential has a slope in the opposite direction and is going to want to push it back out this way. So you can think of this system almost as imagine you took a ball and it just rolls back and forth between these 2 points, right? That's rolling back and forth between rolling in the energy diagram, back and forth between its closest approach and its furthest approach. So we would see an elliptical orbit, right? Here's the gravitating body here. Over here, it's very close, and feeling a force, it's going to want to fling it back out, so it gets flung back out, and then when it's over here at its largest extent, now it feels that force that's going to want to bring it back in. So these two opposing forces, the pseudo force of the angular momentum kinetic energy term, and this actual force of the gravitational potential pointing in the negative direction on the other side. Okay. So where does this energy go? Right, when it's not at one of these extremes, when it's not at its closest approach or its furthest approach, right? It has to conserve energy in total because it's only feeling the force from gravity, so torque is 0, right? So I can't change the total amount of energy in this system. So what happens when this ball rolls down the hill and is down here? Well, that is energy that's going into the other component of kinetic energy, going into the centripetal component of the kinetic energy, and that's why it's gonna get faster and faster and faster as the effective potential energy increases, and then it's gonna slow down, slow down, slow down, slow down, and then it's only gonna have that tangential component, and then it's gonna go back and then only have the tangential component, and et cetera, in this cycle, which gives me my elliptical orbit. Okay? So if I wanted to write the total energy, or rather total mechanical energy, it would be effective potential plus that leftover kinetic energy. We could call that kinetic energy extra if we want. Okay. Now, open orbits, our hyperboloids and paraboloids, they are orbits that are above this energy here. So we could call this the energy bound. Right? Any object that has a total energy below this 0 point here, right? Below 0 kinetic energy plus gravitational potential energy, anything that's below that is bound into an orbit in this system, right? If you think about this as a landscape that a marble is sloshing back and forth in, right? If we're below this line, well, we know by conservation that it's not going to be able, conservation of energy, it's not going to be able to escape. It's going to roll all the way up here, and then it's going to roll back down and back and forth, and then I'll have an elliptical orbit like this. But if we're above this energy of a bound orbit, we have an open orbit. We have a hyperboloid or paraboloid, right, where that orbiting object is coming in from infinity outside the solar system somewhere, gets flung around, right, feels this force when it gets close to here, and then goes back out to infinity. Okay, and it does one cycle and goes back out. So this is a lot like the pendulum that we saw. Energy is being interchanged between these two parts, right? The effective potential energy and the extra kinetic energy. And we have just one stable equilibrium here, right? Which is our circular orbit. Okay. I would stop for questions, but of course none of you are here. So that is the effective gravitational potential. Okay. So if we have more energy, right, enough energy to do something interesting, essentially, we can do some nice calculations. So I'm going to do an example from, I think this is our book. Oh no, it isn't, because it's chapter 11, and in our book, yeah, gravity's chapter 13. So this is a problem from the old book, which I still like. Height of a projectile. A projectile is fired straight up from the south pole of the Earth. So I'm going to south. North is an upside down. Earth. So we're being fired straight up. A projectile is fired straight up from the south pole of Earth with an initial speed of 8 kilometers a second. Find the maximum height it reaches neglecting effects from air resistance. So we're going to find this maximum height via energy conservation. This 8 kilometers a second, though fantastically fast, is not enough to be escape velocity. Right? We saw that previous class when we calculated the escape velocity. So we know that total mechanical energy is going to have to remain constant, right? Because we know that gravity is a conservative force, as we've been seeing. Okay, so that means that our kinetic energy final plus potential energy final equals kinetic energy initial plus potential energy initial. Right, now we just have to fill this in with the stuff that we know. So the kinetic energy final is going to be 1/2 mvf squared. Oops. That gravitational potential energy, that's G mass Earth m r initial equals 1/2 mv initial squared. Oh wait, no, this should be final. I'm sorry. Final minus G mass Earth mass projectile r initial. Okay. So we're asking how far up it goes. So we're looking at the case where at the end it's gone up and up and up and up and it's just stopped and it's coming back down. Okay? So that final velocity when it's at the top is going to be 0. It's not a minus sign, it's a little thing. So this term here is going to be 0. And then we have again G. I'm going to drop the little subscript because it's a pain to write. And then we have our initial velocity, which we're given in the problem. And then when it's just starting out, its radius is going to be the radius of the Earth, right? We take the center of that gravitational system to be the center of the Earth, then we have our Earth there. Okay. So now we multiply through by -1 under or over GMM. So just do a little algebraic rearranging. 1 over RF equals negative the initial squared by 2g mass of the Earth plus 1 radius, radius of the Earth. So now the only thing that really remains to be done is to go find a table and look up the radius of the Earth. Everything else we know. This is the thing we're solving for, RF. Velocity initial is given. G is 6.67 times 10 to the negative 11th. Mass of the Earth, again, is something we can look up. And then we look up the radius of the Earth. So I might as well write both of those things down. So mass of the Earth is 5.98 times 10 to the 24 kilograms, and radius of the Earth is 6.37 times 10 to the 6 meters. Okay, so the Earth is quite heavy and quite big, in case you haven't noticed. And now we want this height max. So there's just one little thing left to do, which is that this height that we're looking for, right, is going to be that final RF minus the radius of the Earth, right? Because we're defining height to be starting at the Earth's surface. So then RF minus our Earth, of course we can simplify this, plug in the numbers, or do it the other way around, and we end up with 6.67, oh, no, just 6 point, that's G, 6.7 times 10 to the 6 meters. Okay. So we can get, by firing this projectile straight up at a really, really fast velocity, we can get it up to more than the radius of the Earth up again, right? Okay. That's kind of neat. Okay. I have one more thing I want to go over before we finish this chapter on gravity, and that is the gravitational field. So far, we've been considering gravitational fields and potentials that are just due to some spherically symmetric astronomical object that's sitting out in space, right? We have the sun, and we'd say, okay, it's vaguely spherically symmetrical. All the mass we assume is concentrated just at that center point, so we treat that gravitating system as just a single point that things orbit around. Likewise, when we talk about the Earth or the Moon, we assume something vaguely spherically symmetrical, and that we take the simplification that all the gravity of that thing, right, is situated, or rather has as its focus the point at the exact center of that exactly spherically symmetric object. Okay. Obviously, not every object is spherically symmetrical, but every object has some gravitational field, right? This whiteboard has a gravitational field that's exerting on me, and I have a gravitational field, and I'm exerting some force on the whiteboard. And it's just that these forces are so tiny that we usually don't notice them, okay? In fact, you can detect smaller gravitational fields if you have very sensitive equipment, okay? So one way that people can detect mineral or oil deposits beneath the Earth, or other stuff that's beneath the ground, is with graviometers, right? Very sensitive devices designed to detect changes in the gravitational field, and you could drive essentially with a graviometer over some surface on the Earth, right? And because different minerals and oil and what have you all have different densities, there's local variations in the gravitational field which you can sense if you have a very sensitive device. So it's important to be able to find the gravitational fields not just of astronomical spherically symmetric objects, but also of other things that have different shapes. Okay? So the way that we talk about the gravitational field of the object, right? Remember, of course, that I have force of gravity equals negative g m r squared r hat. Okay, if we want to write it as a vector. We've got these two masses in here. Typically, in astronomical situations, one mass is much larger than the other mass, and then one is much smaller. So what we do, we have perhaps some irregularly shaped massive object. This is, I don't know what, maybe a giant alien spaceship. Oh, we'll draw the giant alien spaceship from Star Trek 4.